Hey class, so I wanted to talk to you a little bit about thermal conductivity because we didn't really get to it in class today and it is on the homework for this weekend. So I just wanted to talk to you briefly and explain some of the things that we have going on in an equation that you're going to be using on tonight's or this weekend's homework. Alright, so I wanted to start by defining some variables that we're going to be using. H, you'll see, is heat flow. That's the amount of heat that flows. Heat is energy, and when it's flowing in a given period of time, energy over time is power. Okay, so maybe I'll write that too. So power, which I believe we've defined already in class, but I just want to make sure you know, power is energy over time. So it's really a rate, I can't spell apparently, energy over time. It's really a rate at which energy is being consumed or expended. Okay, so energy over time. And so power is measured in watts because watts, 1 watt is 1 joule over 1 second. So the units for our heat are going to be watts. That's heat flow. K is thermal conductivity, which I'll describe in more detail in a minute, but it's really how good something is at conducting thermal energy or heat, right? So as we talked about today, good conductors are things like copper and other metals. Bad conductors are things like plastics and so on. I'll show you in class, but you know, for example, something like copper has a thermal conductivity of 380 watts per meter time Kelvin, so that's a higher one. Something really low like air, for example, is a good insulator. Its thermal conductivity is 0.025. Other things like glass is an insulator, 0.8. Okay, marble 2.5, all different values really, and so I'll give you some more examples in class. So that's thermal conductivity. Area is just cross-sectional area, or really the area through which the heat is transferring, and then D is the thickness. So the equation that we have that you're going to be using tells us that heat transferred, H, is equal to your thermal conductivity, K, multiplied by the temperature difference, delta T, between the two sides. I didn't put that in the variables because we've seen temperature difference many times. Multiplied by A, your area, and then divided by D, the distance or thickness. So this equation can be used in a lot of different ways. You'll see it here in an example in the homework problem, where we use it to look at the heat flow through a blanket. It can also be used, like for example today in class, right? I had that metal rod and I held one end over the flame, and so if you had a flame here, you know, what you might be looking at is the thermal conductivity as the heat moves from one side to the other. So your heat is going to go this direction. So this would be your cross-sectional area, and then your thickness or distance D would be the distance over which it's transferring. So if it starts here, and if I'm trying to see how much heat gets all the way down here, that's where D, the longer it is, the less heat's going to transfer. Delta T is the temperature difference. So say the flame that's touching it, you know, right here, you might have a temperature of, I don't know, 300 degrees Celsius or something. Then over here we might be at room temperature, which is 20 degrees Celsius. So that would determine our temperature difference. Cross-sectional area would be the area just cutting through the rod. And thermal conductivity is something you'd have to be given. Now that's one situation. Another one you're going to see in class, all right, we're going to look at, let's say, a house, okay? How much energy does a house lose? Well, if you're looking at a house, then your area for the house is actually the area of all the walls and ceiling added together. Okay, K would be the thermal conductivity of the wall and insulation combined together. Delta T would be the temperature difference from outside to inside. So in the winter, you know, it might be something like 3 degrees C outside and you're trying to keep it at 21 degrees C on the inside, so your temperature difference would be something like 18. And D would be the thickness of your walls. So it really depends, lots of different applications, but this here is the equation we're going to be using. Heat flow, measured in watts or power, is equal to your thermal conductivity K times your change in temperature T multiplied by your area through which the heat is transferring, and divided by d, the thickness over which that transfer is taking place. So let's look at the homework question number 10 that this applies to. So we're told we have a blanket, all right? We're told how thick the blanket is, so maybe I'll start labeling my variables here. So we're told our thickness of our wool blanket D is 0.015 meters. I'm converting to meters right away from centimeters. And we're told that the blanket has a total 1 meter width, 2 meters long. So our area, which is going to be width times length, our area is going to be equal to 2 times 1, which is 2 square meters. All right. And we're told that the thermal conductivity is 0.07, so I'm not going to rewrite that since we're giving it to it right here, and that it's -5 degrees C outside, and you want to stay warm at 20 degrees C. So our delta T, our change in temperature, is going to be a difference of 25 degrees Celsius, and so 1 degree Celsius is the same change or the same magnitude as 1 Kelvin. Now the numbers aren't the same, right? At 20 degrees Celsius, that's 293 Kelvin, but the change, the difference, since 1 Kelvin and 1 Celsius are the same magnitude, this is the same as 25 K difference in temperature. So with that, it really becomes a plug and chug, right? We just use our equation H. The heat is going to be equal to, again, our K value times our change in temperature multiplied by our area and divided by our thickness. So all those values are given here. I'm going to trust your ability to calculate and get some number, and of course, boom, always box worthy. All right? So then the next question is not what is the rate at which heat is flowing, but how much total heat energy is lost during a night. So say there's 8 hours and that's the temperature outside and you're trying to keep warm that entire time. What is your total energy being lost or given off during the night? Well, as I mentioned earlier, power is energy over time. And if you want energy, well, energy then by algebra is going to be equal to power multiplied by time, which is what I gave you as this hint here. Okay, so what that means then is our energy is going to be equal to whatever we get from the part above, H, multiplied by our time. Now our time we're told is 8 hours, but 8 hours isn't the right units. If you recall, let me just flip back up here, I mentioned a watt is a joule per second, right, as we see over here. And so what we need is not to have hours, but rather to have seconds. Oh, Gus is excited. That's my dog, Gus. All right, well, I think Gus has calmed down now after a brief pause. So coming back to this problem here, yes, we need our time not in hours, but in seconds. So convert your 8 hours to seconds, again, by multiplying 60 seconds are in a minute and 60 minutes in an hour. So you should be able to figure out the total energy after you go ahead and multiply your hours to get to seconds, and then you just take your heat answer from A, multiply it by your time in seconds, and you'll get the total number of energy. And since watts are joules per second, again, we're going to have some number of joules as our answer. Okay, so the units that you should get there are joules, and that'll be, once again, a box-worthy answer. So, part C asks, is this the total energy you will lose during the night, or would you lose more or less? Explain. Oh, Gus is making more noise. What a good boy. Anyway, so I'm not going to give you the answer to part C. There's no calculation or anything. It's a conceptual question. Think about it. Is there any other way that you might conduct heat away from your body other than just through this blanket that is laying on top of you? Okay, is there anything else that might cause you to lose heat? Yes or no, why or why not? That's what you'll tackle in part C. So, talk about that. Let me know if you have any questions. And again, feel free to replay the beginning of this to better understand thermal conductivity and heat flow. And we'll tackle it more in class as well on Monday. Have yourselves a box-worthy weekend, and yeah, hopefully we'll get a little sunshine or something. Gus says have a good weekend also. All right, bye.